This is the real trajectory of Voyager 1, the fastest, farthest, and oldest machine humanity has ever built, and what physics tells us actually happens to it over the next 1 trillion years. If you like deep space stories that stay grounded in real numbers instead of guesses, stick around and consider liking and subscribing so more of these find their way to you. Right now, in 2026, Voyager 1 is the most distant object any human hand has ever touched. It launched from Cape Canaveral on September 5, 1977, 16 days after its twin, Voyager 2, lifted off the same pad. Both spacecraft were born out of a proposal from the 1960s called the Grand Tour, an idea built around a rare alignment of the outer planets, the kind of alignment that happens only once every 176 years, where a single spacecraft could use the gravity of one planet to slingshot itself toward the next, and the next after that, without needing enormous amounts of onboard fuel. Engineers in the early 1970s looked at that alignment and realized it was a once-in-a-career opportunity, a window that, if missed, wouldn't open again until long after everyone working on the project had retired. Budget cuts trimmed the original ambition down from a full grand tour of the outer planets to just Jupiter and Saturn, and for a while, Voyager 1 wasn't even called Voyager. It carried the working name Mariner 11, a footnote from an era when NASA still thought of it as just another entry in the long-running Mariner program, the same family of spacecraft that had already visited Venus, Mars, and Mercury. By the time engineers finished the design, the spacecraft looked and functioned so differently from anything else in the Mariner lineage that it needed a name of its own, and Voyager was what stuck. It's worth remembering just how different the world was the last time this particular planetary alignment was usable. The previous window, roughly 176 years before 1977, fell in the early 1800s, decades before the telephone, the light bulb, or powered flight existed anywhere on Earth, long before anyone had even confirmed the existence of Neptune, which itself wasn't discovered until 1846. Nobody in that era had any way of knowing the alignment was even useful, since spaceflight of any kind was still more than a century away. The next equivalent window won't arrive again until sometime in the 22nd century, meaning the small team of scientists and engineers working at NASA in the early 1970s were operating inside a genuinely once-in-several-lifetimes opportunity, fully aware that if they missed the launch window, no one alive at the time, and likely no one born for generations afterward, would get another realistic shot at a mission quite like it. Nearly 50 years later, Voyager 1 is still flying, and that fact alone is worth sitting with for a moment before moving on to anything else. It was built with technology that feels almost prehistoric by today's standards, technology that was already considered modest by the standards of its own decade. Its 3 onboard computers share a combined 68 kilobytes of memory between them, less than the size of a single low-resolution photograph on a modern phone, less memory than it takes to store a few paragraphs of plain text at high fidelity. The processors inside run at 250 kHz, a clock speed thousands of times slower than an ordinary laptop built in the last decade. Commands travel up to the spacecraft at 16 bits per second, a rate so slow that sending a single short sentence of text at that speed would take longer than making a cup of coffee. The science data it sends back to Earth typically arrives at around 160 bits per second, a transmission rate slower than the dial-up modems people used to connect to the internet in the 1990s, back when a single photograph could take minutes to load one line at a time. And yet this machine, built by engineers who assumed it would go quiet after 15 years at the absolute most, is still talking to us, still returning data, still doing science almost half a century after launch, decades past the point anyone involved in building it expected to still be receiving a signal. It is worth sitting with that gap in capability for a moment, because it says something about the nature of this whole mission that pure statistics can sometimes miss. Voyager 1 was assembled using slide rules and hand-soldered circuit boards, using engineering knowledge that predates the pocket calculator becoming a common household object, let alone anything resembling a modern computer. Every single one of its instructions had to be planned out years in advance, with almost no room for improvisation once the spacecraft was too far away for a quick, easy fix. And yet none of that primitive technology has been the limiting factor in how long the mission has lasted. It was never the computers that set the clock on Voyager 1's working life. It was never the cameras, or the antenna, or the thrusters. The only thing that was ever going to end this mission, from the very first day of planning, was the slow, patient, unstoppable decay of a chunk of radioactive metal sealed inside 3 generators bolted to the spacecraft's frame, ticking down according to a schedule set by nuclear physics long before Voyager 1 ever left the ground, a schedule no amount of clever engineering could ever meaningfully change. Its early achievements are the part most people already know, at least in outline, even if the details tend to blur together. In March of 1979, Voyager 1 swept past Jupiter, coming within about 349,000 kilometers of the planet's cloud tops, and in doing so, it caught sight of something nobody expected to find: active volcanoes erupting on Io, one of Jupiter's 4 large moons, the first confirmed volcanic activity ever observed anywhere in the solar system beyond Earth itself. Before that flyby, most scientists assumed moons were geologically dead, frozen relics with no internal heat, left to power anything as dramatic as an eruption. Io proved that assumption wrong in a single set of photographs, revealing plumes of sulfur and sulfur dioxide being flung hundreds of kilometers above the moon's surface, driven by the constant gravitational flexing Io experiences as it squeezed between Jupiter's immense gravity and the pull of neighboring moons. Voyager 1 also revealed that Jupiter, like Saturn, had a ring system of its own, just an extremely faint one, thin enough and dark enough that it had gone completely unnoticed from Earth for centuries of telescopic observation. That ring wasn't found by accident either. Members of the Voyager imaging team, including Ed Stone himself, had noticed some odd, hard-to-explain readings during earlier planning and proposed a long-shot search for a ring system, even though mission managers at the time were skeptical enough that they only agreed to a single photographic attempt. On March 4, 1979, that one exposure found the ring exactly where the team had predicted, and within days, a ground-based observatory in Hawaii had confirmed it. The ring turned out to be about 9,000 kilometers across, but only 30 to 35 kilometers thick, with a sharp, well-defined outer edge, and its faintness compared to Saturn's rings is largely why nobody using an Earth-based telescope had ever managed to spot it before. During the same encounter, Voyager 1 also discovered 2 entirely new Jovian moons, later named Metis and Thebe, and captured close-up images of the Great Red Spot in extraordinary detail, close enough to resolve individual cloud features as small as 160 kilometers across, revealing what had looked from Earth like a single static blob to actually be an enormous, complex, counterclockwise storm, one that has been swirling continuously since at least the 1830s, when it was first clearly documented. Across the full encounter period, Voyager 1's cameras captured almost 19,000 individual images of Jupiter and its moons. Perhaps the most startling single discovery, though, came from Io itself. As Voyager 1's photographs came streaming back to Earth, engineers realized they were looking at active volcanic eruptions actually in progress, happening in real time as the spacecraft passed by. Plumes of material being flung hundreds of kilometers above Io's surface, while the cameras were still pointed at it, rather than evidence of some ancient, long-dormant geological history. Then, in November of 1980, Voyager 1 swung past Saturn, and the flyby delivered a second wave of firsts. It studied the moon Titan up close, confirming that Titan was wrapped in a thick, hazy atmosphere made mostly of nitrogen, a detail that made Titan the only moon in the solar system known to have a substantial atmosphere at all, thick enough that Voyager's cameras couldn't see through it to the surface underneath. It mapped out the staggering complexity of Saturn's ring system in far more detail than any Earth-based telescope ever had, revealing structure within structure, gaps and braids and ripples that scientists would spend years trying to fully explain. It discovered 5 moons around Saturn that had never been catalogued before, including small ones later named Atlas, Prometheus, and Pandora, moons that turned out to be quietly shepherding the rings into their sharp, well-defined edges through their own gravity. Voyager 1's instruments found that Saturn's atmosphere was made up mostly of hydrogen, with roughly 11% helium and only faint traces of other gases, and they clocked wind speeds inside that atmosphere reaching up to 1,100 miles per hour, while also pinning down the planet's rotation period with new precision, at 10 hours and just over 39 minutes. Up close, the rings turned out to be far stranger than any Earth-based telescope had ever suggested. Instead of a few broad, simple bands, Voyager 1 found thousands of individual, tightly packed ringlets, some only a few hundred meters wide, along with a bizarre, thin outer ring, the F-ring, that appeared braided, twisting several separate strands around each other in a way that shouldn't have been physically possible under simple orbital mechanics, a puzzle that would take scientists years, and eventually a follow-up mission called Cassini, to properly untangle. Just as strange were what scientists nicknamed spokes, wedge-shaped, transient smudges of fine dust that would appear and then vanish again across the rings over the course of just a few hours, seemingly held in place not by gravity, but by some kind of electromagnetic interaction nobody fully understood at the time, and one that, to a real extent, is still not completely explained even now. Titan itself turned out to be just as full of surprises. Voyager 1 made its closest approach to the Moon in the late hours of November 11, 1980, passing less than 310,000 miles away, close enough that scientists genuinely hoped its cameras might finally see straight through the Moon's hazy atmosphere down to a solid surface. They couldn't. The haze was simply too thick and too opaque at visible wavelengths for any camera on board to punch through. Instead, researchers turned to a radio signal bounced through Titan's atmosphere and back, using the way that signal bent and weakened to calculate the atmosphere's density and pressure indirectly. What they found was a surface pressure about 1.6 times that of Earth's, a surface temperature hovering around 93 to 95 degrees Kelvin, somewhere near minus 290 degrees Fahrenheit, and an atmosphere made up overwhelmingly of nitrogen, with roughly 10% methane and fainter traces of other hydrocarbons like ethane, acetylene, and propane. For a brief moment during the analysis of that radio data, planetary scientist Carolyn Porco has since recalled an early, ultimately mistaken interpretation of the numbers led to a hushed rumor circulating among the Voyager science team at JPL that liquid nitrogen might actually be pooling on Titan's surface. The initial reading turned out to be wrong, but the broader excitement it sparked wasn't, because the real data still pointed towards something almost as remarkable: a moon cold enough and chemically rich enough that lakes of liquid ethane, with methane dissolved inside them, seemed entirely plausible. That single flyby, and the tantalizing mix of what it did and didn't manage to reveal, is largely what convinced NASA and the European Space Agency, years later, to send an entirely new mission, Cassini, along with a lander called Huygens, back to Titan for a much closer look. That Saturn flyby did something else too, something that would end up shaping the rest of Voyager 1's existence, far more than any of its scientific discoveries. Because the mission planners specifically wanted a close look at Titan, the trajectory needed to bend the spacecraft up and out of the flat plane that all the planets orbit within, sending it on a course angled well above the solar system's disk. That decision meant Voyager 1 would never again pass close enough to another planet to receive a gravity assist. No more course corrections from flybys, no more bending its path with a convenient boost from a planet's gravity. From that point in November of 1980 onward, Voyager 1 has been moving in essentially one long, uninterrupted line, curving only very slightly under the weakening pull of the Sun's gravity, heading up and out of the solar system entirely. Behind both flybys was a single scientist who would go on to define the entire mission far more than any individual instrument or photograph. Edward Stone, a space physicist who had been running Caltech's Space Radiation Lab, was recommended for the role of Voyager project scientist in 1972, 5 full years before either spacecraft actually launched. He held that position, the only person ever to hold it, for exactly 50 years, stepping down in 2022 while remaining a professor emeritus at Caltech. Across that half-century, Stone oversaw the Jupiter and Saturn flybys covered so far, along with Voyager 2's later encounters with Uranus in 1986 and Neptune in 1989, making the Voyager program the only mission in history to have visited all 4 giant planets. He did all of this while simultaneously serving as director of the entire Jet Propulsion Laboratory from 1991 to 2001, overseeing dozens of other missions at the same time, including the Pathfinder mission that landed NASA's first Mars rover, Sojourner, in 1996. Colleagues who worked alongside him for decades described him as calm, exacting, and endlessly curious, someone who, by his own account, simply wanted to understand and measure and observe the universe around him for as long as anyone would let him. Stone passed away on June 9, 2024, at the age of 88, a little less than 2 years after formally retiring from the role. Voyager scientist Linda Spilker, who had worked on the mission since its original planetary flybys, succeeded him as just the second project scientist in the mission's entire history. It is a strange thing to consider. Ed Stone spent 50 years, essentially his entire working life, guiding a pair of spacecraft that are still out there right now, in 2026, continuing a journey he set in motion before either probe ever left the ground. A journey that will now, by every indication, continue on long after Stone himself, and everyone else currently working on the mission, is gone. One of the most quietly powerful moments in the whole mission came a decade later, in February of 1990, when Voyager 1 was already about 6 billion kilometers from home, far beyond the orbit of Neptune. At the request of scientist Carl Sagan, who had been pushing for the idea for years against some internal resistance from engineers worried about wasting precious power and risking damage to the camera by pointing it near the sun, the team turned the spacecraft's camera back toward the inner solar system and captured a series of 60 photographs, later assembled into what's known as the family portrait, a set of images showing 6 planets from a distance no human eye had ever seen them from before. In one of those frames, Earth appears as a single pale speck, less than a single pixel wide, caught inside a stray beam of sunlight scattered across the camera's optics purely by chance. It became known as the pale blue dot, and it remains one of the most reproduced images in the history of space exploration, precisely because of what it doesn't show. No cities, no oceans, no borders, no evidence of the 7 billion or so people who called that speck of light home. Just a dot, suspended in a beam of light, in the middle of an otherwise empty photograph. Shortly after taking it, engineers switched off Voyager 1's cameras for good, not because anything had broken, but because every watt of remaining power needed to go toward keeping the spacecraft alive and communicating, not toward pictures nobody was ever going to ask it to take again. It is easy to describe that photograph in terms of pixels and pointing angles and stray light, and all of that is technically accurate. But it misses what actually made the image resonate with people the way it did, and still does today. Every person who has ever lived out their entire life, felt joy, felt grief, fallen in love, raised a child, fought a war, built something that mattered to them, or simply gotten through an ordinary Tuesday, did every bit of that on the single speck of light captured in that one frame. Sagan spent years afterward writing and speaking about what that photograph meant, returning to the same basic idea again and again, that from far enough away, every quarrel, every border dispute, every triumph and every tragedy in human history collapses down into something smaller than a single pixel, lit only because it happened to catch a beam of sunlight scattered at just the right angle. Voyager 1 did not set out to make a philosophical point. It was simply following a camera command, executed automatically, at a distance where the instructions were already hours old by the time the shutter clicked. But the resulting image ended up saying something that no scientific instrument was really built to say, and it is part of why, even decades later, people who have never read a single technical paper about the mission still recognize that photograph on sight. The pale blue dot turned out to be the last photograph Voyager 1 would ever send home. From there, the story becomes less about discovery and more about endurance, a shift in the nature of the mission that would come to define everything that followed. In February of 1998, Voyager 1 quietly passed Pioneer 10, an earlier NASA probe that had launched years before it, and became the most distant human-made object in existence, a title it has held every single day since, and one that grows a little more secure with each passing year as the gap between it and every other spacecraft ever launched continues to widen. In 2004, it crossed something called the termination shock, the boundary where the solar wind, the constant outward stream of charged particles flowing off the sun, starts to slow abruptly under pressure from the interstellar medium pushing back from outside. And on August 25, 2012, it crossed the heliopause, the true outer edge of the Sun's protective bubble of particles and magnetic field, becoming the first spacecraft in history to leave the heliosphere entirely and enter true interstellar space, the vast region between star systems that isn't shaped by any single star's influence at all. It's worth being precise about what that actually means, because it gets misunderstood constantly, even in otherwise well-researched coverage of the mission. Leaving the heliosphere is not the same thing as leaving the solar system. The Sun's gravity reaches vastly farther than its magnetic influence and its solar wind ever do, stretching out to the edge of the Oort cloud and beyond. Voyager 1 is still, right now, gravitationally bound to a solar system it will technically remain a part of for tens of thousands of years yet, even though it has already crossed into a region of space where the Sun's particles and magnetic field no longer dominate the environment around it. It left the neighborhood, in other words, long before it left the house. The scale of that remaining distance is genuinely difficult to overstate. The Oort cloud's outer boundary, the point at which the Sun's gravity finally becomes too weak to hold on to anything at all, is generally estimated to sit somewhere between 1 and 2 light-years from the Sun, roughly a quarter to half the distance to Proxima Centauri, the nearest star system beyond our own. Voyager 1, even after nearly 50 years of continuous flight, has covered only a tiny fraction of that remaining gap. The heliopause crossing in 2012 was a genuine milestone, the first time any human-made object had ever measured the boundary of the Sun's direct influence directly. But it was really only the end of the beginning, a doorway out of the Sun's immediate atmosphere rather than an exit from its gravitational household altogether. What Voyager 1 has actually been doing out there, in the space between stars, for the 14 years since crossing the heliopause, is listening. In December of 2018, NASA reported that the spacecraft had picked up a persistent, low hum, a kind of constant drone, in the ionized gas of the interstellar medium, the faint background noise of plasma vibrating in the space between star systems, a sound no instrument had ever recorded from that far out before. In 2020, Voyager 1 detected something scientists hadn't fully anticipated, a noticeable increase in the strength of the magnetic field around it, a hint that the Sun's magnetic influence might extend and occasionally flex outward, farther into interstellar space than researchers had assumed possible, for a boundary that was supposed to mark the Sun's absolute limit. There's a reason that plasma wave instrument had to carry so much of the burden of proving Voyager 1 had actually reached interstellar space in the first place. An earlier, more direct plasma density instrument on board had already failed years before, shortly after the Saturn encounter back in 1980, long before the spacecraft ever got close to the heliopause. Without it, scientists had to rely on indirect evidence instead, waiting for rare moments when energetic bursts of electrons happened to excite plasma oscillations that the plasma wave instrument could actually pick up and measure. The oscillation frequencies scientists eventually recorded corresponded to an electron density of roughly 0.08 to 0.11 particles per cubic centimeter, a number that matched almost exactly what astrophysicists had already calculated should exist in the interstellar medium, and stood in sharp contrast to the far less dense plasma inside the heliosphere. It took researchers more than a year of collecting these rare, scattered readings before they felt confident enough to conclude that Voyager 1 really had crossed into interstellar plasma, even though the crossing itself had already happened months earlier. That density measurement matters beyond just confirming the heliopause crossing, because it tells us something concrete about the emptiness Voyager 1 is now moving through. A density of roughly 1/10 of a particle per cubic centimeter is almost impossible to picture using everyday intuition, but it means the spacecraft is now drifting through a region of space that is, for all practical purposes, close to a perfect vacuum, disturbed only by the faintest whisper of scattered particles and the occasional pressure wave sent rippling outward whenever the Sun has a particularly active outburst. These aren't dramatic headline discoveries in the way Io's volcanoes or Titan's atmosphere were. They're the kind of quiet, patient data collection that only a machine willing to keep working for decades past its expected lifetime could ever produce. Small pieces of evidence slowly accumulating in a region of space no other instrument has ever sampled. That patience has not come without real cost, and the mission has come close to ending more than once in just the past few years. In 2023, Voyager 1 started sending back garbled, unreadable data, the result of a corrupted chip inside its flight data system. A fault, occurring roughly 15 billion miles from the nearest engineer who could physically touch the hardware causing it. NASA's team spent months working the problem, partly because every single command they sent and every response they received back had to travel for the better part of a day each way, turning even a simple diagnostic test into a process that unfolded over what felt like an agonizingly slow back and forth. They eventually devised a software patch, rerouting the corrupted portion of the code to a different, still functioning section of memory elsewhere on board. An improvised fix built for hardware that had been sitting in deep space for nearly half a century. By April of 2024, Voyager 1 was talking normally again. Then, in October of 2024, a fault protection routine triggered unexpectedly right after engineers turned on one of the spacecraft's heaters, and the spacecraft automatically switched away from its primary X-band radio transmitter over to a backup S-band system, a transmitter that hadn't been used since 1981, more than 4 decades earlier. For a stretch of weeks, the team wasn't entirely certain they'd be able to recover the primary system at all. Each of these incidents followed roughly the same emotional shape for the small team of engineers still assigned to the mission. A problem appears, often with no obvious cause, transmitted across a gap that already takes most of a day to cross in each direction. The team runs through possibilities using decades-old documentation, some of it written by engineers who have since retired or, in Ed Stone's case, passed away, none of whom are available to simply ask. A fix gets proposed, uploaded, and then everyone waits, sometimes for the better part of a week, simply to find out whether the patch worked or made things worse. It's a style of engineering that barely exists anywhere else on Earth anymore, closer to something out of the early space race than to modern spacecraft operations. Precisely because almost nothing else humanity has ever built has been asked to keep functioning, and keep being fixed from 250,000 times farther away than the Moon, for anywhere near this long. There is also a detail from this same stretch worth mentioning, because it shows just how thin the margin for error has become. Between May of 2025 and February of 2026, only a single antenna on Earth, Deep Space Station 43 in Canberra, Australia, was capable of sending commands to Voyager 1 at all. One dish, on one continent, was the sole link capable of reaching the most distant object humanity has ever built. Engineers did eventually restore full X-band communication and resumed normal data collection by mid-November of 2024. But each of these incidents has served as a reminder of exactly how fragile this 50-year-old connection really is. Every one of these recoveries has bought Voyager 1 more time, but time is exactly what it is running out of. And the reason comes down to physics, not engineering, meaning no software patch will ever be clever enough to solve it. The spacecraft is powered by 3 radioisotope thermoelectric generators, devices that convert the heat produced by the natural radioactive decay of plutonium-238 into usable electricity. Plutonium-238 has a half-life of about 87.7 years, which means its heat output, and by extension, Voyager 1's electrical power, is shrinking a little every single day, in a slow, steady decline that no repair or clever workaround can ever reverse, because it is baked directly into the nuclear physics of the fuel itself. NASA has said the generators lose roughly 4 watts of usable power every year. To compensate, engineers have spent decades quietly switching things off, one system at a time, in careful order of scientific priority, sacrificing lower-value instruments to keep the most important ones alive a little longer. The cameras went first, back in 1990, right after the pale blue dot photograph. The cosmic ray subsystem, an instrument that had been measuring the energy of particles streaming through interstellar space, went dark in February of 2025. The low-energy charged particle instrument followed in April of 2026. As of the time of this video, only 2 science instruments remain active on Voyager 1 at all: the magnetometer, which tracks magnetic field strength and direction, and the plasma wave subsystem, the same instrument that picked up that eerie interstellar hum back in 2018. Each of those earlier shutdowns represented a real decision, made deliberately by the small team of remaining Voyager engineers, weighing which piece of science still mattered most against how many more months or years of power it would buy for everything else. There was no dramatic announcement when the cosmic ray subsystem went dark in February of 2025. No headline event, just a quiet command sent across billions of kilometers, switching off an instrument that had been continuously measuring the energy of interstellar particles since before most of the people currently working on the mission were born. The low-energy charged particle instrument that followed in April of 2026 had its own long history too, having helped confirm, back in 2012, that Voyager 1 really had crossed the heliopause in the first place. Powering it down meant giving up the ability to keep directly sampling the kind of particle data that first proved the spacecraft had entered interstellar space at all, a trade the team made anyway, because keeping the magnetometer and the plasma wave instrument alive a little longer mattered more. NASA's current estimate is that Voyager 1's generators may supply enough power to return basic engineering data until somewhere around 2036, though that figure depends entirely on how carefully the remaining systems continue to be managed, and it could shift earlier or later depending on what fails next. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has described the spacecraft's remaining hardware in stark terms, explaining that everything left on board is what engineers call single string, meaning there are no backups left at all for any of it. No redundant system waiting to take over if the primary one fails. Some of Voyager 1's small hydrazine thrusters, the tiny jets responsible for keeping its antenna precisely pointed at Earth across 25 billion kilometers of empty space, have already developed clogging problems in their fuel lines, and there is no spare thruster system left to take over if the remaining ones fail too. If the antenna were ever to drift out of alignment with Earth for any reason, even briefly, the mission would end immediately, not because the spacecraft itself had broken, but because we would simply lose the physical ability to hear anything it still had to say. There is no single official day marked on anyone's calendar for when that silence is expected to arrive, and that uncertainty is deliberate, a reflection of just how much the mission's remaining lifespan depends on small, unpredictable factors: a clogged thruster line, a random cosmic ray flipping a bit in 50-year-old memory, one more unexpected fault triggering one more automatic safe mode from which the spacecraft might or might not recover. When the moment does come, whenever it comes, there will likely be no dramatic final message, no last transmission designed for the occasion. Most likely, a scheduled signal simply won't arrive on time, and after enough repeated silence, after enough failed attempts to re-establish contact, the small remaining team at JPL will begin to accept that Voyager 1 has, at last, gone quiet for good. It is a strange kind of ending for a mission this significant. Not a single defined event, but a slow, ambiguous fade, confirmed only in hindsight, sometime after the fact, once enough silence has accumulated to rule out one more delayed signal, one more temporary glitch, one more improbable recovery. And that brings us to a milestone happening right now, in the same year this video was made. Sometime around the middle of November 2026, NASA projects that Voyager 1 will cross a distance of exactly one light day from Earth, roughly 25.9 billion kilometers, or about 16.1 billion miles. It will be the first human-made object in history to reach that distance. To put that number in terms that are almost impossible to feel intuitively, consider a few comparisons drawn straight from NASA's own framing of the milestone. If you climbed into an ordinary car and drove at 50 miles an hour without ever stopping, it would take you almost 37,000 years to cover that same distance. Even flying continuously at the speed of a commercial passenger jet, roughly 550 miles an hour, the trip would still take about 3,300 years. And using the distance NASA's Artemis program travels on a single round trip to the moon as a yardstick, you would need to make that same round trip about 34,000 times over to add up to the distance Voyager 1 has already covered. Light itself, the fastest thing in the universe, will need a full 24 hours just to cross the gap between Voyager 1 and home once that milestone is reached. Suzanne Dodd explained the practical reality of that gap simply, in an interview, describing what happens if she sends a message to the spacecraft on a Monday morning. She won't hear anything back until Wednesday morning, because the signal needs a full day to reach Voyager 1, and any reply needs another full day to travel back. When Voyager 1 hits that one light day marker, it will be 5.6 times farther from Earth than Neptune, the outermost planet in the solar system, currently is. And even after nearly 50 years of continuous flight, covering a distance of 16 billion miles, Voyager 1 will have traveled only about 0.0027% of the way to Proxima Centauri, the nearest star system beyond our own. It is an almost impossibly small fraction, and it says everything about just how empty and how large the space between stars actually is. It helps to place that one light-day figure alongside a few other communication delays humanity has already lived through, because the growth in scale from one to the next is genuinely staggering. During the Apollo moon landings, viewers watching the grainy footage live could hear roughly a 2.5-second gap between an astronaut's comment and mission control's reply, the result of a signal needing about 1.3 seconds to cross the roughly 226,000 miles separating the moon from Earth. Send a signal to Mars instead, and that delay stretches to as much as 4 minutes, depending on where the two planets happen to sit in their orbits. Reach out to Jupiter, and the delay grows to as long as 52 minutes each way. Pluto pushes it further still, up to about 6.8 hours. None of those numbers come anywhere close to Voyager 1's growing gap, which by November of 2026 will require a full 24 hours in each direction, a round-trip conversation lasting 2 entire days. It is a big part of why deep space missions closer to home, landers and rovers exploring Mars in particular, are built with so much onboard independence, capable of making their own split-second decisions rather than waiting on instructions that might arrive minutes too late to matter. Voyager 1 has no such independence built into it, at least not in any modern sense. It runs on programming written and finalized decades before any of today's autonomous systems existed, executing a fixed set of stored routines rather than making anything resembling a real-time decision on its own. Every meaningful choice about its operation, from which instrument to prioritize to how to respond to a fault, still passes through human hands on Earth first. Hands belonging to a team that has to plan every command around the knowledge that whatever they send will not arrive, and will not be acted upon, for a full 24 hours, and that any consequence of that command, good or bad, won't be visible back on Earth for a second day after that. It is a strange, patient, almost old-fashioned way to run a spacecraft in an era when most new missions are built to think for themselves, and it works only because the team overseeing Voyager 1 has spent decades learning to plan several moves ahead, the way a chess player might, rather than reacting to problems as they happen. Making that one light-day conversation possible at all depends on a piece of infrastructure most people never think about. NASA's Deep Space Network, a system of large radio dish antennas positioned roughly 120 degrees apart around the globe, in California, Spain, and Australia, spaced deliberately so that as the Earth rotates, at least one dish is always pointed toward Voyager 1, no matter the time of day. Signals from the spacecraft arrive so faint by the time they reach Earth, spread out and weakened across billions of kilometers of empty space, that receiving them cleanly often requires linking multiple antennas together at once, combining their collected signal the way a person might cup both hands around their ears to catch a distant, barely audible sound. The fragility of that whole listening chain became especially clear during a stretch between May of 2025 and February of 2026, when only a single antenna anywhere on the planet, Deep Space Station 43 near Canberra, Australia, was capable of sending commands up to Voyager 1 at all. For the better part of a year, one dish, on one continent, quietly held the entire line of communication between Earth and the farthest thing humanity has ever built. Once its power finally runs out, likely sometime in the 2030s, Voyager 1 will not shut down in any dramatic or sudden sense. It will simply go quiet, one final signal fading into nothing, with no announcement and no warning beyond whatever gradual power decline engineers are already tracking in advance. No more 24-hour conversations, no more Monday to Wednesday exchanges between a spacecraft and the small team of people on Earth still listening for it. But here is the detail that makes this story fundamentally different from almost every other piece of retired human technology ever built. Voyager 1 does not stop moving when it goes silent. It does not rust because there is no oxygen out there to rust it. It does not burn up because there is no atmosphere to create the friction needed for that. It does not fall into anything because there is essentially nothing left nearby with enough gravity to pull it in. Interstellar space is close enough to a true vacuum that there is nothing left to slow it down at all. No air resistance, no meaningful drag of any kind, nothing but the faintest trace of stray particles scattered so thinly across such enormous distances that their effect is functionally zero. The sun's gravity is already far too weak at that distance to ever pull the spacecraft back toward home. Once the power dies and the instruments fall permanently silent, Voyager 1 will keep moving at almost exactly the same speed and along almost exactly the same line it is on right now, coasting silently through the dark for as long as the laws of physics allow, carrying with it a golden record designed by a committee led by Carl Sagan, a 12-inch, gold-plated copper disc etched with sounds, music, and images meant to describe what life on Earth was like at the moment it launched, addressed to no one in particular, and in a strange way, to anyone at all who might ever find it. Before following that trajectory any further, it's worth spending a little more time with the object actually making the journey, the golden record itself, because it is arguably the most human part of this entire story. Putting it together took almost a year, under enormous time pressure, led by a small committee at Cornell University chaired by Carl Sagan. Sagan brought in Frank Drake as technical director, the same Frank Drake known for the Drake equation, along with Anne Druyan as creative director, artist John Lomberg handling the visual content, writer Timothy Ferris producing the audio, and Linda Salzman Sagan coordinating the spoken greetings. Together, they assembled 116 images, encoded in analog form directly into the grooves of the record, one of which was simply a calibration circle included so that whoever eventually played the record would know how to correctly interpret the images that followed. Alongside the images, they added natural sounds recorded from across the planet: surf, wind, thunder, the calls of birds, and the songs of humpback whales taken from a 1970 recording by researcher Roger Payne. Layered over the natural sounds were more ordinary, human ones: footsteps, laughter, a mother's kiss, a baby crying, small fragments of daily life stitched together into a short audio collage, often referred to as the sounds of Earth. Then came the greetings, spoken in 55 different languages, opening with Akkadian, a language spoken in ancient Sumer roughly 6,000 years ago, and closing with Wu, a modern Chinese dialect still spoken today. The very first voice on the record belongs to Kurt Waldheim, who was serving as Secretary General of the United Nations at the time, followed by a short greeting from then-President Jimmy Carter. Nearly all the other greetings came from ordinary people, recruited quickly from Cornell's language departments once plans to record. United Nations delegates ran into scheduling problems the team simply didn't have time to solve. The English language greeting, the simple line, "Hello from the children of planet Earth," was recorded by Sagan's own 6-year-old son, Nick, who reportedly wasn't told at the time how significant that brief recording would turn out to be. After the greetings comes roughly 90 minutes of music, deliberately assembled to avoid leaning too heavily on any single culture or era. Johann Sebastian Bach ended up the most represented composer, with several pieces included, alongside Beethoven, Mozart, and Stravinsky. The committee also included Blind Willie Johnson, Louis Armstrong, Peruvian panpipes, a Navajo night chant, a Georgian folk song, percussion from Benin, and Chuck Berry's Johnny B. Good. A choice that caused some genuine friction within the committee at the time, with folklorist Alan Lomax reportedly objecting that rock and roll felt too immature for a message meant to represent all of humanity. According to accounts from people involved, Sagan's reply was short and simply pointed out that plenty of humanity's population happened to be young. One frequently repeated claim, that the Beatles' "Here Comes the Sun" was blocked from the record, traces back to real interest from both Sagan's team and the band members themselves, but ultimately, the recording rights were withheld by the record company, not because of any dispute between Sagan and the Beatles directly. Each golden record is protected inside an aluminum cover, along with a cartridge and needle and a set of symbolic instructions etched directly into the surface, explaining in diagrams, not words, how the record is meant to be played. A small sample of uranium-238 was electroplated onto that cover as well, included specifically to function as a radioactive clock. Because uranium decays at a known, fixed rate, anyone who eventually finds the record and understands basic physics could measure the remaining ratio of uranium to its decay products and calculate, with reasonable accuracy, exactly how long the spacecraft had been traveling by the time it was found. Carl Sagan, reflecting on the entire project, offered a line that has stuck with the mission ever since, saying only that launching this kind of bottle into the cosmic ocean says something hopeful about life on this planet, regardless of whether it's ever actually found by anyone at all. That last part matters, because the odds of the golden record ever being found and played by another civilization are, by any honest accounting, vanishingly small. Voyager 1 isn't aimed at any particular star system with any particular chance of harboring life. It is simply drifting, following a trajectory shaped entirely by decades-old planetary flybys, carrying its message past whatever happens to lie along that path, whether or not anyone is there to receive it. In that sense, the golden record was never really built for aliens in the first place, or at least not only for them. It was built, in large part, as a message to ourselves, a snapshot of what one committee of people, working quickly under real deadline pressure in the late 1970s, decided was worth saving and sending outward if nothing else of us ever survived. So the honest question becomes what happens to that silent, coasting spacecraft next, and where its motion actually carries it. The nearest confirmed answer, and the only part of this story NASA has calculated in any real detail, involves a small red star. Voyager 1 has not even reached the Oort cloud yet, the enormous, distant shell of icy objects that marks the true gravitational edge of the solar system, first proposed by Dutch astronomer Jan Oort back in 1950 as an explanation for where long-period comets originate. NASA estimates the spacecraft will begin entering the inner edge of the Oort cloud in roughly 300 years from now, and that it will take about 30,000 years just to cross all the way through it, a region so vast that even at Voyager 1's considerable speed, the crossing alone will take longer than the entire span of recorded human history, repeated many times over. Only after that long, slow passage through the Oort cloud will Voyager 1 truly be free of the solar system's gravitational grip in any meaningful sense. It's worth pausing on just how strange that timeline actually is. Voyager 1 has already been flying for nearly 50 years, longer than most human careers, longer than most marriages, long enough that the engineers who designed it have mostly retired, and in Ed Stone's case, passed away. And by the Oort cloud's own accounting, the mission has not even really started the next leg of its journey yet. 300 years from now is itself a span longer than the entire history of the United States as a nation, and that 300-year mark is only when Voyager 1 begins entering the Oort cloud, not when it finishes crossing it. The 30,000-year crossing that follows is longer than the entire span of human civilization since the invention of agriculture. And even after all of that, the spacecraft will only then be considered free of the sun's gravitational influence in the fullest sense, a threshold so far beyond ordinary human timekeeping that it barely functions as a date at all, more a kind of distant horizon than a moment anyone could ever mark on a calendar. From there, its existing trajectory bends it toward a star currently known as Gliese 445, also catalogued under the older designation AC plus 79 3888. Right now, in our present moment, Gliese 445 sits roughly 17 light-years from Earth, but it is not standing still, and neither is anything else in the galaxy. It is a red dwarf star, an M-type main sequence star with roughly a quarter to a third the mass of our own Sun, and it is rushing toward the solar system's current position at roughly 120 kilometers per second, more than 10 times faster than Voyager 1 itself is moving. In about 40,000 years from now, give or take a few thousand depending on exactly which calculation you trust, Voyager 1 will find itself closer to Gliese 445 than it currently is to our own Sun. At its nearest approach, the spacecraft will pass within roughly 1.6 to 1.7 light-years of that star, a distance that sounds enormous, and genuinely is, but which still counts as a real, measurable close encounter on the scale of interstellar distances. NASA itself has put the comparison simply. It took 35 years for Voyager 1 to reach interstellar space in the first place, but it will take 40,000 years just to get closer to another star than it currently is to its own. It is worth pausing on the irony buried inside that encounter, because it is the kind of detail most documentaries skip past entirely. Voyager 1 was never aimed at Gliese 445. No engineer ever chose that star as a destination, and no course correction was ever made to steer the spacecraft toward it. Mission planners only discovered the coincidence more than a decade after launch. Once Voyager 2 had finished its own planetary flybys, and someone on the team finally sat down to calculate exactly where Voyager 1's existing, already fixed trajectory would eventually lead over the coming tens of thousands of years. It turns out Gliese 445 is not approaching because Voyager 1 is heading toward it. It is approaching because it is moving through the galaxy along its own independent path, a path that happens to bring it into the Sun's neighborhood during roughly the same tens of thousands of years that Voyager 1 will be drifting through that same patch of interstellar space. Two objects, moving for entirely unrelated reasons, on trajectories set in motion by completely separate forces, are simply going to pass close to one another purely by chance, the way two cars on different highways might happen to cross the same intersection at the same moment without either driver ever intending to meet. Voyager 1's twin, Voyager 2, is following its own separate path through the same general region of the galaxy, and its story offers a useful point of comparison. Around that same 40,000-year mark, Voyager 2 is expected to pass within roughly 111,000 astronomical units of a star called Ross 248, another red dwarf, this one carrying only about 12% of the Sun's mass and just 16% of its radius, a much smaller and dimmer star than even Gliese 445. The two Voyager probes, launched 16 days apart from the same launch pad, chasing different planets on different trajectories, will end up making their nearest stellar approaches to two completely different stars, on similar but not identical timescales, decades after both spacecraft have gone permanently silent. It is a small, almost poetic detail that the two spacecraft, born from the same design, built side by side, launched from the same pad within 2.5 weeks of each other, will spend the overwhelming majority of their existence drifting apart from one another, each carrying an identical golden record, each heading toward a different anonymous red star, never to be anywhere near each other again. Voyager 2 took the longer, more ambitious route through the solar system, going on to become the only spacecraft in history to fly past Uranus in 1986 and Neptune in 1989, discovering unusual tipped magnetic poles at Uranus and towering ice geysers erupting from Neptune's largest moon, Triton, reaching heights of about 8 kilometers, more than 100 times taller than Old Faithful's tallest recorded eruption in Yellowstone. Because it took that longer path through the outer solar system, Voyager 2 ended up moving slightly slower than its twin, and it crossed into interstellar space 6 years after Voyager 1 did, in November of 2018. Both spacecraft are still operating today, still returning what data they can, still slowly losing power at roughly the same rate. Two nearly identical machines that spent their first decade together, making an almost unimaginable string of discoveries, and are now destined to spend the rest of their existence, however long that turns out to be, moving farther and farther apart, alone, in opposite directions, through the same otherwise empty galaxy. After the Gliese 445 flyby, official, NASA confidence level predictions basically run out entirely. What comes after that point is described only in general, statistical terms, rather than any specific mapped-out sequence of encounters. NASA has said that a spacecraft drifting freely through the galaxy, with no further course corrections, will encounter other stars at roughly the same rate the Sun itself does, as it makes its own long orbit around the galactic center, meaning more close stellar passages are essentially guaranteed to happen over a long enough stretch of time, even if nobody has actually mapped out exactly which stars or exactly when. Some independent, less formally verified estimates, circulated among space enthusiasts, rather than published through NASA itself, suggest that a few 100,000 years from now, Voyager 1's path could bring it within roughly a light year of a much more obscure star, catalogued as TYC 3135 52-1, though this particular figure comes from amateur trajectory calculations rather than an official NASA source, and should be treated as a rough, lower confidence estimate rather than a confirmed prediction on the same footing as the Gliese 445 numbers. Beyond that point, the trail of officially calculated numbers simply ends, not because Voyager 1 stops moving, but because nobody has published a detailed star-by-star map of its position for the next million years, let alone the next trillion. To go any further with this story, it becomes necessary to set the spacecraft itself aside for a while and ask a much larger question instead. What is the galaxy around it, and the universe surrounding that galaxy, actually going to be doing on a timescale that long? The honest answer to that question starts close to home, with our own Sun. Right now, the Sun is a little less than halfway through its expected life as a hydrogen-burning star. In roughly 5 billion years, it is expected to exhaust the hydrogen fuel in its core, swell dramatically into a red giant large enough to engulf the inner planets, and eventually shed its outer layers entirely, leaving behind a dense, slowly cooling stellar remnant called a white dwarf. 5 billion years sounds vast on any human scale, and it is, but on the time scale this video is actually asking about, it is practically nothing at all, a single early chapter in a book, with an almost incomprehensible number of pages still left to turn. Long before the Sun even reaches that late stage of its life, something else is already scheduled to happen. Astronomers expect the Milky Way to collide with our neighboring galaxy, Andromeda, in roughly 4 to 5 billion years, merging the two into a single, larger galaxy that some researchers have taken to informally calling Milky Way. Galaxy collisions sound catastrophic on the surface, and in certain respects they genuinely are, but individual star systems inside colliding galaxies rarely crash into one another directly, because the space between stars is so vast, even within a single dense galaxy, that actual physical collisions between solar systems remain extremely unlikely, even during an event as large as an entire galactic merger. It is entirely possible, based on current modeling, that whatever remains of our solar system by that point, and whatever remains of Voyager 1's ancient, decades-old trajectory through it, could survive that merger essentially undisturbed, simply reshuffled into position within a new, larger, combined galaxy. It's a counterintuitive idea worth explaining a little further, because most people picture a galaxy collision the way they'd picture two cars colliding, crumpling metal, shattering glass, mass destruction on impact. Galaxies don't really work that way. A galaxy like the Milky Way is, by volume, almost entirely empty space, with its hundreds of billions of stars separated from one another by such enormous distances that the actual density of matter, averaged out across the whole disk, is closer to nothing at all than to anything resembling a solid object. When two galaxies merge, what actually collides is mostly gravity and gas and dust, vast clouds of interstellar material slamming together and igniting bursts of new star formation, while the individual stars themselves, including whatever the Sun has become by then, mostly just sail past one another, nudged onto new orbits by the changing gravitational landscape, but essentially never actually touching. It's less like a car crash and more like two enormous, loosely packed crowds of people walking through each other at a busy intersection. Plenty of jostling and rerouting, but very few actual collisions. To understand what happens across the much longer stretch of time after that merger, it helps to borrow a framework that astrophysicists Fred Adams and Gregory Laughlin laid out in their book, The 5 Ages of the Universe, first published in 1999, a book that remains one of the most detailed popular attempts to map the entire future of the cosmos, using known physics rather than speculation alone. Adams and Laughlin divided the entire future of the universe into 5 broad eras, based on what kind of physical process dominates the cosmos at each stage. We are currently living inside the second of those 5 eras, called the Stelliferous Era, quite literally, the age filled with stars. An era that began a few 100 million years after the Big Bang and is expected to continue for an almost unimaginable length of time yet, far longer than it has already lasted. According to Adams and Laughlin's model, the Stelliferous Era does not actually end until galaxies run out of the raw hydrogen gas needed to keep forming new stars, and even the slowest burning, most fuel-efficient stars remaining in the universe finally exhaust what little fuel they have left. Those slow-burning stars are called red dwarfs, the same broad category of star as Gliese 445, and they turn out to be remarkably stingy with their fuel compared to larger, brighter stars. Despite being smaller and dimmer individually than stars like our Sun, red dwarfs are so numerous throughout the universe, and they burn their hydrogen so slowly and so efficiently that their combined mass actually outweighs all the larger, brighter stars in the universe put together. Some of the smallest, longest-lived red dwarfs are expected to still be quietly shining 10 trillion years from now, according to Adams and Laughlin's calculations, long after every sun-like star and every larger star in the universe has already died, exploded as a supernova, or quietly collapsed into a stellar remnant. By their model, the stelliferous era does not fully come to a close until the universe is somewhere around 100 trillion years old, the point at which even the very last red dwarfs finally go dark, and star formation, as an ongoing cosmic process, simply stops happening anywhere at all. It helps to picture what that actually looks like, star by star, rather than just as an abstract span of years. Somewhere in that stretch of time, long after our own sun has died and cooled into a white dwarf, long after the Milky Way and Andromeda have fully merged and settled into a single, calmer galaxy, individual red dwarf stars, each one smaller and dimmer than our sun ever was, will still be sitting quietly in the dark, fusing hydrogen into helium at a pace so slow and so miserly that a single one of these stars could keep shining for roughly 1,000 times longer than the current age of the entire universe. There is no dramatic ignition, no explosive beginning the way larger stars are born inside the collapsing clouds of a nebula. Most of the smallest red dwarfs that will ever exist have, in a sense, already been born, quietly formed sometime in the universe's first several billion years, and simply have that much fuel left to burn. Gliese 445, the very star Voyager 1 is heading toward, sits within this same broad category, a modest, unremarkable red dwarf by every measure except one, that in about 40,000 years it will become the closest star to a 50-year-old machine built by a species that, on any of these timescales, will have been gone, in its current form, for a very, very long time. It's worth briefly sketching out what Adams and Laughlin's model says happens after the stelliferous era finally ends too, not because Voyager 1 is likely to be around to see any of it, but because it helps put the trillion-year figure in this video's title into real perspective. Once star formation stops entirely, somewhere around 100 trillion years from now, the universe moves into what they call the degenerate era, an age dominated by stellar remnants rather than active, fusing stars. White dwarfs, the collapsed cores left behind by stars like our Sun, become the most common object holding onto ordinary matter in the universe during this period, slowly cooling over unimaginable stretches of time. Every so often during the degenerate era, two white dwarfs drifting through a galaxy will collide, triggering a supernova explosion bright enough to briefly light up an otherwise darkening universe. On rarer occasions, two brown dwarfs, failed stars too small to have ever ignited proper fusion on their own, will collide and merge into something massive enough to finally start fusing hydrogen, essentially creating a brand new, low-mass star long after ordinary star formation has otherwise ceased everywhere else. According to Adams and Laughlin's model, even the white dwarfs themselves are not permanent. Toward the end of the degenerate era, current physics predicts that protons, one of the basic building blocks of ordinary matter, will begin to decay, a process so slow that it hasn't been directly observed in any laboratory or experiment, but one that current particle physics models suggest is real, unfolding over a timescale reaching out to the 39th cosmological decade, meaning 10 to the power of 39 years. Once that process finishes, what remains transitions into the black hole era, a period stretching out to roughly the 100th cosmological decade, a number so large it's often compared to a googol, in which black holes become the last significant structures left in the universe, themselves slowly leaking away through a process called Hawking radiation, until nothing large enough to be called an object remains at all. Whatever comes after that, the so-called dark era, is described by Adams and Laughlin only in the broadest, most tentative terms, a thin, cold scattering of particles with barely any physics left worth discussing in any concrete way, laid end to end. The sheer span of these eras makes even a trillion years look modest by comparison. If the entire history of the universe so far, all 13.8 billion years of it, were compressed down to a single second, the stelliferous era we currently live inside would still have roughly 7,000 more of those seconds left to run before it ends. The degenerate era that follows would stretch on for a span so much longer that expressing it in the same compressed timescale becomes almost meaningless, and the black hole era after that pushes the numbers into territory where cosmologists themselves generally stop trying to offer any kind of relatable comparison at all, simply presenting the exponents on their own and letting them speak for themselves. 1 trillion years, the number sitting in this video's own title, is real, and it is almost incomprehensibly long by any ordinary human measure, and it is still, by any honest accounting, only a small early step into a future that current physics says stretches out very much further still. Here is what that framework actually means for the specific number sitting in this video's title. 1 trillion years sits comfortably inside that stelliferous era, nowhere near its end. Star formation, according to most current models, is still technically ongoing at the 1 trillion year mark, even though it has slowed down dramatically compared to the much more active fireworks of the early universe, back when galaxies were forming stars at a far faster pace than they do today. Red dwarf stars, including ones physically similar to Gliese 445, are still expected to be burning steadily and quietly at that point, sitting comfortably partway through lifespans that stretch out to 10 trillion years or more. If Voyager 1's fragile hardware could somehow physically survive 1 trillion years of constant, low-level cosmic radiation, the occasional micrometeorite impact, and the sheer, slow, erosive patience of deep time itself, which is an enormous and almost certainly false assumption to make about a 50-year-old machine built from 1970s materials, it would still, in principle, be drifting through a galaxy that has stars in it, light still being produced somewhere out there, physics still recognizably similar in its broad strokes to the physics we understand and rely on today. What would be dramatically, almost unrecognizably different by that point is everything surrounding that galaxy. This is where the research of Harvard astronomer Avi Loeb becomes directly relevant to the story. Loeb has spent years studying what dark energy, the mysterious force accelerating the expansion of the universe outward in every direction, does to the view from inside a single galaxy over extremely long timescales. Because dark energy pushes space itself apart, and does so faster and faster as time goes on, rather than slowing down the way gravity alone would predict. Other galaxies are not simply moving away from our own, they are accelerating away, continuously picking up speed relative to us. Eventually, given enough time, they will end up receding from us faster than light itself can cross the growing gap between us. And once that threshold is crossed, their light can never reach our galaxy again, no matter how sensitive or how powerful our telescopes eventually become. Loeb first outlined this problem in a paper written back in 2002, and the idea gained wider public attention around 2011, notably reported after Loeb reportedly worked through the underlying calculations at length during a Harvard snow day, rather than treating it as a passing thought experiment. Loeb has specifically used 1 trillion years as a benchmark figure in his research, using it to illustrate a future in which our own galaxy, the merged combination of the Milky Way and Andromeda, ends up functionally alone within the observable universe, with no other galaxies visible from it at all. A single lit island surrounded by darkness, with no other islands anywhere in sight. Loeb has explained that future astronomers looking outward that far into cosmic time would see only their own galaxy's stars, with no direct way to observe any evidence that other galaxies, or even the Big Bang itself, ever actually existed, unless they managed to find some other, more indirect way to reconstruct that lost history from whatever clues happened to remain. In later research, Loeb and his colleagues proposed that so-called hypervelocity stars, individual stars flung out of galaxies at extreme speed after close, violent encounters with the supermassive black holes at galactic centers, might carry indirect evidence of cosmic expansion along with them as they themselves get accelerated outward by dark energy on their own long, solitary journeys. That indirect evidence, Loeb suggested, could potentially give future scientists, whoever or whatever they turn out to be, a way to reconstruct the universe's history and confirm the reality of the Big Bang, even after every other galaxy has permanently faded from view. There is something almost unsettling about that image once it settles in. Right now, tonight, anyone can walk outside, look up, and see thousands of individual stars, and with even a modest telescope, countless faint smudges of light that are actually entire other galaxies, each one containing hundreds of billions of stars of its own. That view, the one every human being who has ever lived has shared in some form, staring up at a sky full of other galaxies, is not a permanent feature of the universe. It is, by Loeb's own accounting, closer to a brief privileged window, a few tens of billions of years wide at most, sitting near the beginning of the universe's history, rather than representing some permanent, unchanging backdrop. Future observers, however far off and however different from us they might be, looking outward from whatever the Milky Way and Andromeda have become by then, would have no way of knowing any of this ever happened just by looking up. They would see one galaxy, their own, and an empty, starless dark beyond it, with absolutely nothing in that view to suggest a Big Bang, an expanding universe, or trillions of other galaxies that had simply drifted too far and too fast to ever be seen again. It is a strange, almost dizzying thing to sit with for a moment. A trillion years from now, assuming the standard picture of cosmology holds up over that much time, our galaxy would very likely still have stars in it, would still have red dwarfs like Gliese 445 quietly burning away, would still operate according to physics that would feel broadly familiar to anyone who understood physics as we understand it today. But it would be utterly, completely alone, surrounded on all sides by a darkness with no other lights left in it. The rest of the universe's roughly 2 trillion currently observable galaxies having drifted permanently beyond reach, their light forever unable to catch up to wherever our galaxy happens to be by then. Not every scientist agrees that this slow, lonely fade into isolation is actually where the universe is headed, and it is worth being honest about that disagreement, rather than presenting one single version of the future as settled, uncontested fact. In September of 2025, a team of researchers, Hoang Nan Liu, Yu-Cheng Chu, and S.H. Henry Tai, published a paper built on fresh survey data drawn from 2 of the most ambitious cosmic mapping projects ever constructed, the Dark Energy Survey and the Dark Energy Spectroscopic Instrument, both designed specifically to measure how dark energy behaves across cosmic time with far greater precision than earlier instruments allowed. Their analysis suggested that dark energy might not actually be a fixed, unchanging force after all, as the standard cosmological model has long assumed, but something dynamic instead, a force whose strength changes over time rather than remaining constant. If that turns out to be true, then instead of the universe endlessly accelerating apart forever, expansion could eventually slow, stop, and then reverse entirely, pulling everything back together in a total collapse that researchers refer to as a big crunch. Their calculations place the universe's total lifespan at somewhere around 33.3 billion years, suggesting that the universe is already sitting roughly at the halfway point of its entire existence right now, rather than standing anywhere near the beginning of an eternity that might stretch out for 1 trillion years or far beyond that. If that particular model eventually turns out to be correct, then the entire premise behind this video's title becomes moot in the most literal sense possible, because there would be no universe left, in any recognizable form, still around to ask the question of where anything might be located within it. It is a genuinely strange position for modern cosmology to be in. For decades, the working assumption among most physicists was that the universe's fate came down to a fairly simple choice. Either it would keep expanding forever, thinning out into cold darkness, or gravity would eventually win out and pull everything back together, and by the early 2000s, accumulating evidence for dark energy had seemingly settled that argument firmly in favor of endless expansion. The 2025 findings did not disprove dark energy itself, and they have not been broadly accepted as the new consensus, but they reopened a question a lot of working physicists had considered closed, using precisely the kind of large, carefully gathered survey data that is supposed to settle these arguments rather than reopen them. That is simply how science operates at its edges, where the data is hardest to gather and the stakes of getting it wrong are highest. A measurement that once looked settled can, with a better instrument or a larger dataset, become unsettled again almost overnight, and the honest response to that is not to quietly ignore the new result in favor of the more comfortable, previously accepted picture, but to say plainly that the matter is now open again and let the following years of research decide it. That is the honest current state of modern cosmology, and it deserves to be presented as honestly uncertain rather than settled. Nobody actually knows, with real certainty, which of these 2 competing futures is correct. The standard model, the one still taught in most textbooks and used as the working assumption in most published research, points toward endless expansion, gradually fading galaxies, and eventually, the kind of cold, dark isolation Avi Loeb has spent years describing in detail. A newer, more contested body of evidence, built from genuinely rigorous survey data, points toward the opposite ending entirely. A universe with a hard, definite stop, arriving far sooner than 1 trillion years, practically around the corner by comparison, in strictly cosmic terms. Both pictures are built from real data, real telescopes, and real physicists doing the most careful work they currently can with what has actually been measured so far. Neither one has been proven, and neither one should be presented as though it has. What we do know, with far more confidence than any of that distant speculation allows, is what is happening to one small machine, right now, this year, as it crosses a distance that light itself needs a full day to cross. Voyager 1 was never built to answer questions about trillions of years into the future. It was built to study Jupiter and Saturn for a handful of years in the late 1970s. Nothing more ambitious than that at the time of its launch. And everything it has done since then, every additional milestone, every recovered signal after a near-fatal fault, every extra instrument switched off simply to buy a little more borrowed time, has been an unplanned bonus, decades upon decades of extra operation that nobody on the original engineering team ever expected to receive. It is, right now, the farthest and the oldest continuously operating spacecraft humanity has ever built, moving at over 61,000 kilometers per hour, carrying a golden message meant for nobody in particular, and for absolutely anyone at all, out toward a red star it was never once aimed at, through an Oort cloud it has not yet even reached, into a future where its remaining power will eventually fail completely, its voice will fall permanently silent, and its motion will simply continue, uninterrupted by anything, for as long as the laws of physics allow that motion to go on. If the standard model of the universe holds up over that immense stretch of time, that continued motion could, in principle, carry Voyager 1 through a galaxy still faintly lit by ancient red dwarf stars 1 trillion years from now, utterly alone in a universe that has otherwise gone dark and silent all around it, with every other galaxy long since faded permanently from view. If the newer, more contested research turns out to be correct instead, the universe itself may not last anywhere near that long at all, and the entire question of where Voyager 1 will be in 1 trillion years might simply never get answered by anyone, human or otherwise, because there would be nothing left in existence capable of asking it. Either way, right now, in November of 2026, Voyager 1 is crossing a full light day of distance from Earth for the first time in human history, still listening through its 2 remaining instruments, still occasionally speaking back across a gap that takes light itself an entire day to cross, the single most distant thing our species has ever built, heading out into a future that even our very best physics can currently only partly see, one that stretches out so far beyond ordinary human experience that 1 trillion years and 40,000 years and 33 billion years all start to blur together into something closer to a single, quiet, ongoing mystery than any kind of fixed, knowable answer. Before stepping back to close this out, it helps to simply sit for a moment with the scale of what has actually been described here, because human beings are not naturally built to hold numbers like these in mind for very long. 1 trillion years is not just a big number attached to a small number, the way 1 million feels like a bigger version of 1,000. It behaves differently from anything in ordinary experience. If you tried to count from 1 to 1 trillion, one number every second, without ever stopping to sleep or eat, the counting alone would take you well over 30,000 years, longer than the entire span of time NASA estimates it will take Voyager 1 just to cross the Oort cloud. Human civilization itself, agriculture, cities, written language, all of it, fits inside a window of roughly the last 10 to 12,000 years, a sliver of time so thin against 1 trillion years that it effectively disappears, the way a single grain of sand disappears against the length of a beach stretching farther than the eye can follow. Modern humans, as a species, have existed for somewhere in the range of 200 to 300,000 years. The universe itself, everything currently observable, everything Voyager 1 has any hope of learning about, is only around 13.8 billion years old. 1 trillion years is roughly 72 times longer than that. It is a length of time so far beyond the universe's own current age that trying to picture it honestly requires setting aside almost every intuition a person builds up over an ordinary human lifetime. And Voyager 1 itself, the actual hardware, the cameras that took the pale blue dot, the golden record bolted to its side, the radio dish still faintly speaking to Earth as of this year, will not be part of that far future in any functioning sense. Its power will fail, its instruments will fall silent. Whatever is left of it, the aluminum frame, the 10-sided bus, the plutonium cores slowly cooling toward absolute stillness, will simply keep drifting, inert, carried by nothing but momentum, through a void so empty that nothing will ever meaningfully act on it again. It will not corrode, it will not break apart, it will not, in any way a person watching from Earth might picture, decay the way objects decay under gravity, weather, and time here on the ground. It will simply continue, a silent, unchanging shape moving through the dark, for longer than anything built by human hands has any right to last, carrying a message that was never really engineered to be read, so much as it was engineered to exist, to keep going, to be there, whether or not anyone or anything is ever there to notice it. It is worth stepping back, before closing this out, to think about what Voyager 1 actually represents, separate from any of its specific instruments or milestones. It is, at its core, an object built by a relatively young species, on a relatively young planet, orbiting a relatively ordinary star, sent outward with no real expectation of ever being retrieved, and very little expectation of even being heard from this far into the future. Every fact laid out across this video, the launch date, the flybys, the pale blue dot, the slow decline of its plutonium power source, the one light day milestone arriving this same year, the future encounter with Gliese 445 in roughly 40,000 years, exists on a timescale that is, in the end, staggeringly small compared to the trillion-year figure in this video's own title. 40,000 years sounds enormous by any ordinary human measure, and it is, but set against the 10 trillion-year lifespans of the smallest red dwarf stars, or the 100 trillion-year span before the stelliferous era finally ends, it barely registers as a fraction of a fraction. Even the entire span of Voyager 1's active operational life, less than 60 years from launch to eventual silence, is a rounding error small enough to effectively vanish against a timescale measured in trillions. And that gap between what we can actually measure and calculate with real confidence and what we can only model, extrapolate, and reasonably guess at is really the honest shape of this whole story. We know, with a very high degree of confidence, exactly where Voyager 1 is today, how fast it is moving, and roughly when its power will finally run out. We know, with somewhat less certainty but still solid confidence, that it will pass near Gliese 445 in roughly 40,000 years, and that it will keep moving afterward, indefinitely, carried by nothing but its own existing momentum through a vacuum with nothing left to slow it down. Beyond that point, the specific, detailed picture fades into general statistical reasoning about stellar encounter rates, and beyond that, it fades further still into competing cosmological models that current science has not yet been able to settle, with real, credentialed physicists actively disagreeing about whether the universe even lasts long enough for a trillion-year question to have any meaningful answer at all. There is something worth sitting with in that honest uncertainty, rather than rushing past it toward a tidier conclusion. Most science communication is built around the comfort of a clean answer, a single number, a definitive result, a case closed. This story does not offer that, and pretending otherwise would misrepresent exactly the kind of careful, sourced accuracy this video set out to maintain from the very beginning. Voyager 1's near future, the Oort cloud, the slow approach toward Gliese 445, the eventual silence sometime in the 2030s, is about as well understood as anything in deep space exploration gets. Its distant future, the part actually promised in this video's title, is not a fact waiting to be reported. It is a genuine, live, unresolved question sitting at the edge of modern physics, one being actively argued over in journals and conferences by scientists who have devoted entire careers to narrowing it down, and who still, honestly, do not agree. What can be said with confidence is this: whatever happens to the wider universe, whether it keeps expanding into darkness the way the standard model predicts, or whether it eventually reverses and collapses back in on itself, the way the newer, contested research suggests. Voyager 1 itself will keep moving in a straight, uninterrupted line for as long as there is a universe left for it to move through. Nothing out there is waiting to stop it. No friction, no collision, no force strong enough to interrupt momentum that has already carried it past every planet in the solar system, past the heliopause, and soon past a distance that takes light itself a full day to cross. That simple physical fact, more than any single number or date in this video, is the closest thing to a real answer the question in the title actually has. Voyager 1 will keep going, quietly, unless or until something in the structure of the universe itself intervenes. That, in the end, is where this story actually leaves us. Not with a single, confident answer to the question in the title, but with the most honest version of what modern science can currently offer. A spacecraft, still faintly alive, still sending back the last whispers of data from farther away than anything else humanity has ever built, carrying a golden record meant to speak for an entire species long after everyone who built it is gone. Moving forward through the dark on a trajectory partly known and mostly unknown into a future that might stretch out for 1 trillion years, filled with the last light of dying red dwarf stars, or might not stretch out nearly that far at all, depending on which version of the universe turns out to actually be true. Somewhere out past the orbit of Neptune, moving at over 61,000 kilometers per hour, is a machine built almost 50 years ago, using less computing power than a modern kitchen appliance, carrying a golden record full of whale songs and bark and a 6-year-old boy saying hello on behalf of the entire planet. It has already outlived nearly everyone who built it. It has already traveled farther than any human-made object in history, farther than Pioneer 10, farther than anything currently on a launch pad anywhere on Earth. Within the next few years, its last instruments will fall quiet. Its last signal will fade below the noise floor of even the most sensitive antenna humanity can point at it, and it will become, for all practical purposes, just another object drifting through the galaxy, indistinguishable from a rock or a comet to anything that might one day pass near it without already knowing what it was. And still it will keep moving, past Gliese 445 in 40,000 years, past whatever comes after that, star by star, encounter by encounter, on a schedule too long and too uncertain for any human institution to track, through the merger of the Milky Way and Andromeda, through the slow fade of every other galaxy in the sky, beyond the reach of any possible telescope, through the last light of the last red dwarf stars, if the standard model of the universe holds, or through nothing at all, if the newer, more unsettling research turns out to be right instead. Nobody currently alive will ever know which future actually happens. But right now, in 2026, the spacecraft is still out there, still moving, still carrying its quiet golden message outward into a darkness that has no name and no known end. And that, more than any specific number, is the real story of where Voyager 1 is headed.